I can't start with the space bar. I have to click it first, and then we're good. So apologize. I just hit space bar and it like ends the stream. Because yeah, my like Streamlabs Twitch thing, yeah. Right. So the last program I was using was not PowerPoint; it was this guy, and spacebar just. So anyway, now, so again, BOD stuff. So we have an example to get us started, just to kind of make sure we're making sense of what exactly we're actually looking at. So I'm going to give you just a minute to do this. It's pretty straightforward, but it'll make you start thinking about solving the problems, which I think will be helpful. So we have a 10 milliliter sample of sewage mixed with enough water to fill a 300 milliliter bottle. So we could draw that up, perhaps. The initial dissolved oxygen in the bottle is 9 milligrams per liter. And then to help assure an accurate test, it is desirable to have at least a 2 milligram per liter drop in dissolved oxygen during the 5-day run. And the final DO should be at least 2 milligrams per liter. So basically, our our dissolved oxygen probe is not great in some sense, right? We have to make sure we have at least 2 milligrams per liter change in dissolved oxygen observation in order to trust that the instrument is working well. And we also have to make sure that we have at least 2 milligrams per liter remaining, again, because we're not so confident about the detection limit. Probably probes will be a little more accurate, but for this scenario, that's what we're given. So that means we have some specific range of wastewater strength that we could manage to observe, right? So that's the task. So I'll give you a couple minutes to work on that. Remind you here that P is the volume of wastewater divided by the total volume. And then our BOD equation here looks like this. Take a minute on that. just it's both. All right, so you can kind of see I've done most of it so far. The P is 10 over 300, 300 milliliters total in the volume, which is dilution plus wastewater. It's because we filled a 300 milliliter bottle. 10 is the volume of the wastewater. If we needed the volume of dilution, that should be 300 minus 10, right? 290, but don't really need it. So P is 10 over 300 or 1 over 30. We know the DO initial is 9. So I went ahead and set up both the min and the max to get kind of our range here, boundaries, as the equation is simply going to be 9 minus something divided by 1 over 30. So in the minimum case, we had to have at least a drop of 2, so we could either say that is just a drop of 2 over 1 over 30, or we could calculate back and say, well, 9 minus that minimum drop of 2 should be 7, right? So that would be the minimum case. That gives us 2 divided by 1 over 30, which is 2 times 30, which is 60. So minimum then should be 60 milligrams per liter of BOD. And the maximum, we do the same thing, and we said we have to have at least 2 remaining. This number on the right, this DO final, that's what's remaining after the 5 days. So that's 9 minus 2 is 7, times 30 is 210. Okay. Makes sense? All right, so quite simple when we put it all out there, but there's some thought to be had there about, okay, how is this working if we're checking that minimum versus the maximum, all of that. Okay, so in reality, we usually are dealing with pretty high strength wastewater. If you realize that, we covered kind of in the intro to wastewater strength can go all the way up to 500 or so milligrams per liter of BOD. So that's quite a lot of substrate, and a 1 to 30 dilution was not sufficient to process that, right? We need perhaps at least double that 1 to 30. So there is going to be cases where we have very, very little of our actual wastewater in our bottle because we have to dilute it so much. What happens if we do that and we're using this nice, clean, pure lab water is now we don't have enough microbes. And so it's going to take several days for the microbes to even multiply to the point where they can consume it at a rate that would be similar to what they would do in the environment. Because there's plenty of microbes floating around in the environment that are happy to consume stuff. So given that, when we do a BOD test in our bottle, we have to add microbes to our dilution water. And when we do so, inevitably there's some microbe food in there because we had to grow the microbes. Some of the microbes have died and dissolved, so now there's some organic molecules floating around. So ultimately, when we add dilution for a high-strength wastewater, we're almost always adding some more BOD. which is just kind of annoying because then we have to calculate that. So we'll see in a minute, but basically what we'll do is we'll do 2 BOD tests at the same time. One will be with our bottle of just dilution water, which shouldn't have a lot of BOD, but it'll have a little bit. So then we can know exactly how much BOD is in our dilution water, and then we'll do the mixture. The mixture just being, what we typically measure, that DO initial minus DO final. That M here is the mixture. So we're going to observe the mixture. That'll be something, if we've got wastewater here and the rest of it's dilution water. We're seeding the dilution, right? So this microbial seed, so to speak, provides plenty of microbes, but also adds a bit of BOD in the dilution. So to deal with that, a little bit of algebra here. One thing we'll note here is that, okay, our P we've defined already. We can take a 1 minus P. This is going to be the fraction that is dilution. So if P is the fraction that is wastewater, then 1 minus P is the fraction that is dilution water, right? And that's going to be VD over the mixture. We could say that as VD over VD plus wastewater. Should be pretty straightforward. That's going to come back in a moment when we solve for how to find the BOD of the wastewater from this equation. This equation here is that very simple mixture type mass balance equation that we've seen all along, all sorts of times, right? So we have a concentration times a volume. We've done this with concentration times flow rates with 2 streams meeting, stuff like that. So this is going to be, this concentration times volume is going to give us milligrams BOD, because the volumes will cancel, equals milligrams BOD added from the wastewater plus milligrams BOD added from the dilution. Right, so we could say that's the milligrams BOD coming from wastewater and milligrams. So that's just kind of straightforward, makes sense, right? This is just what's in there as a total in the mixture is equal to the contribution of the wastewater plus the contribution of the dilution water. Okay, that's all I'm saying here. This is your standard V times C kind of stuff, right? It's, if we take a look at the units. So VD times BOD in the dilution. Could also write volume wastewater times BOD for the waste. Okay, so given that, we have this little mass balance equation. We say the total amount in the mixture is from those two. So now we need to solve for how do we get an equation to find the BOD of the wastewater, which is ultimately why we are doing the test in the first place, right? The whole reason to do the study, to do the measurement, is to understand the strength of the wastewater or what's happening downstream. Okay, so we're going to take that equation and really just solve for it here. And I'm just going to do line by line kind of how the book goes about it. So we're going to divide everything by volume of the wastewater. That'll get the BOD wastewater by itself. We'll also go ahead and move it to one side. So we get BOD wastewater equals BOD of the mixture times the volume of the mixture. And that's here divided by volume of the wastewater, because we divided everything by that. Minus BOD of the dilution times the volume of dilution, again divided by volume of the wastewater, because we were separating that. Okay, so that's step number one. And from here, we can see we're pretty much there. But the book likes to get everything in P, and it turns out that's reasonably convenient, as we'll see the final solution. But we can take this volume of the mixture divided by the volume of the wastewater. That's just 1 over P, right? That's the inverse of P, because P by itself is the volume of the wastewater divided by the volume of the mixture. So that should be 1 over P here. Then over here, we have this volume of dilution divided by volume of the wastewater. And I'm sure that we could expand this out with some algebra, but I'm just going to say the book says it, so it must be right. That expansion would look like 1 minus P divided by P. Okay, and of course we could write all that out and prove to ourselves that the book is right. So given that, we can write all of this as, we see a common denominator here with the P's. We can write it as BOD of the mixture minus BOD of the dilution times the fraction that is dilution, which makes sense, that 1 minus P, all divided by P. So at the end of the day, it looks quite similar to what we were working with at the beginning, but here we have accounting for the BOD and the dilution. Okay, so you'll have that, or actually it might be the next form of it, on your equation sheet. So as I mentioned, we're going to do this in 2 experiments. And so we're going to have 2 different dissolved oxygen conditions to think about when we're doing measurements. So we'll have one with the mixture and one that's completely dilution water. So this one's full, and this one has it's full also, but some of that is wastewater and some of that is dilution water, right? So I'll just say we have some volume of the wastewater and some volume dilution. This entire thing is volume of dilution. Okay, so we're going to do these 2 experiments at the same time. So we have 2 different measurements happening, and in order to keep them straight, we have a new label here that the book provides, arbitrarily B. Okay, B is our second dissolved oxygen metric. That's for the dilution bottle. So BI is the initial DO in the dilution vial. And B final is, BF is B final. That would be the final DO in the dilution vial. Okay, so pretty straightforward. It's just a random use of B. I guess if we treat this as A, then this is B. Maybe it makes sense. So that's it, right? So all we need to know is what happens in the second bottle, and then we can understand the entire BOD in the wastewater given that. So just algebra to get from where we were earlier to dealing with 2 systems. Okay, so let's do this then. A test bottle containing just seeded water has its DO level dropped by 1 milligram per liter in a 5-day test. Separately, a 300 milliliter BOD bottle is filled with 15 milliliters of wastewater and the rest seeded dilution. And sometimes this could be expressed as a 1 to 20 dilution. And that one experiences a drop of 7.2 milligrams per liter in the same time period. So the question is, what would be the 5-day BOD of the waste? So take a couple minutes, make sure you can put those things together for an answer here. So solve this problem. As you see, I set up, went ahead and got P, 1 over 20 is 0.05. So 1 minus P is 0.95. So I can go ahead and set up the equation here like this, where we have essentially what this DO initial minus DO final. This is the drop in the mixture, right? This is the DO drop. That's how we could define it for the mix. And so that was given to us as 7.2. So it doesn't really matter what initial we had, and the fact that we weren't given any initial, because we knew the drop. And here was 1.0 for the drop in the dilution vial. So that means it becomes pretty simple here then. 1 times 0.95 is just 0.95. So we'll get a calculator real quick. So we can say that 7.2 minus 0.95 is 6.25. And really, we're just multiplying by 20 here to get our final answer. So 125 milligrams per liter BOD. In the 5 days. Okay. Does that make sense? Issues? All right. Okay. So from here, essentially looking downstream next, what we want to know is what's going to happen to the dissolved oxygen. We're also going to deal with oxygen deficit, and actually later we're just going to use D for deficit. So I'll just clear that up a little bit now. So basically, when we take a look at a stream or river, it's going on some path, and if we assume that the velocity is pretty much constant throughout, then time becomes approximately the same as distance. And the system is approximately a plug flow reactor. So what we can do is look at what's happening with the oxygen demand in a given part and compare that with the reaeration. So if we have some amount of reaeration, so the physical process of oxygen gas going from the atmosphere into the water, that's going to compete with the deoxygenation from the microbial processes. And what we're really particularly concerned about is at what point does our dissolved oxygen reach some sort of minimum? And is that going to harm the fish and wildlife? That's kind of the target, is to understand something about that. And typically we've got sort of a saturation point. So we'll call this the oxygen sag curve, and we'll look at a few different things, how they're changing over time. But ultimately, that's kind of the question, is where does that happen and how bad is it, right? So are we completely depriving the stream of oxygen, or is it just 6 milligrams per liter of oxygen instead of 9? Because in that case, 6 milligrams per liter probably supports all fish and wildlife, right? So it's not a big deal. It will also be temperature dependent. So maybe we look at what happens during the summer versus the winter and things like that. The biological activity will also slow down when it's cold. So that could complicate things. Not that we're going to go there. Okay, so one of the common tools to use when taking a look at natural systems like this would be a method called total organic carbon analysis. So essentially, this is getting a quantification of how much CO2 is produced when you essentially burn any organics in the water. You send the water through a system, you heat it really hot. Well, first you scrub it of any CO2 that's dissolved. So you acidify it, drive off all the CO2 you can. Then you take it and say, all right, well, now let's subject it to really, really harsh oxidizing conditions and measure CO2 over time, and you get a good approximation of all of the organic carbon in there. It's very similar to measuring chemical oxygen demand. So we could consider the TOC, this organic carbon, as kind of the substrate or the microbe food. And so after some discharge for wastewater, if there's no other inputs, then it would look something like this over time, right? Eventually we get pretty much nothing, and it's a nice first order decay because microbes are munching on the food. Okay, so as that's happening, that means that our rate of deoxygenation is pretty substantial when there's a lot to munch. And then that's going to go to very close to zero and ultimately reaching zero if we run out of food, right? So that's kind of one concept here. When we compare the competing rates, the rate of which deoxygenation is occurring will decrease as the amount of food decreases. Okay, so when we're going to compare this in terms of TOC and dissolved organic matter, then we'll see a graph that does just that in a minute. Really, what we'll notice is the oxygen sag curve, as we'll call it, is in relevance to some saturation point. So we have, based on temperature and stuff, the DO saturation is up here. And natural river water typically is not quite saturated. There's usually some biological activity happening. It's in natural systems. So normally what will happen if we have, let's say, a discharge of wastewater effluent into a river that is flowing, and it's going to happen at this spot, we'll have some DO in the river, some DO in the wastewater, and sometimes we oxygenate that so it's not directly causing any problems. So this might be saturated, but this might not be. Then we'll have some initial DO here, or some, as we'll see in a minute, initial deficit once they mix. So that means that we have some amount of oxygen here, and as that waste starts being decomposed, we will start removing oxygen from the water. And so from this point, I drew it up earlier, it'll look kind of like that. And then eventually, if no organic matter is ever added, so we're not really considering a true stream or whatever, but we could actually come back to saturation. Typically, we'll reach that small deficit that's kind of natural, right? But this is what it would look like. Eventually, theoretically, you could reach that. So like I said, this is kind of what we're interested in, and it could be a really bad scenario if we have a lot of wastewater where it would look more like that, right? So something like that, that's what we're looking to understand. Okay, so we need then two things. One is what kind of rate equation do we have for the removal? And by the way, before I get too deep into this, what I'm doing today is kind of explaining where the stuff is coming from, not that we're going to derive these ourselves for the problems. Okay, so I'm just going to give you the context. We've seen a lot of rates this semester, we've dealt with them, and we've built mass balances. These are technically the same processes, and so I hope you can appreciate that as we see it, but we're not really going to focus on that part of it so much as just, okay, we have this equation now, how do we apply it? What's relevant to it? Okay, so the rate for the BOD, it's the oxygen demand itself, so the deoxygenation, really depends on the amount of BOD that remains, and when I say BOD, biologically degradable stuff, right? Stuff that will cause oxygen demand. Our rate will depend on how much of that is there. That's kind of that total organic carbon assessment. So we could call that TOC or substrate. Now, mostly we've talked about BOD in a 5-day measurement. 5-day measurement is pretty standard. That's important. But one thing that, if we're not careful, will get confusing is we can think that that's the total BOD in the solution. That's not actually true, because we could also do a BOD for 10 days. That would be a larger number than a BOD for 5 days. We gave it more time, there's more oxygen demanded, right? Because in 5 days, the bacteria don't eat everything, they just eat a fair amount. And 5 days is just practical, so we do 5 days. So when we talk about BOD with this letter L, that's BOD remaining. So that's BOD. So if we say L naught here, this initial BOD, that's the amount remaining at time 0. Basically, like when we discharge wastewater into the river, we call that time 0. That's going to be equal to BOD if we let the BOD bottle go for an infinite amount of time. Okay? So that means the most amount of oxygen that could ever be demanded by this stuff at an infinite amount of time. So that means that this infinite amount of BOD, not infinite amount, BOD at an infinite time, we can call that the amount remaining at some time t plus the amount of BOD that was measured and already removed at that time t. So we could say if there's a total of 100 milligrams per liter, so if 100 milligrams per liter BOD total, that's going to be L naught. And we measure BOD 5 equals 70 milligrams per liter, then L at time 5 should be 30, right? I'm just writing it out to be very clear here. It should be very easily intuitive once I write all that out, but it can get confusing, which is why I want to just take the time to say that. Okay, so this L value then is that remaining after some amount of time. So we can then map or look at dLt dt, so the change in the amount that's remaining over time is equal to this first order decay reaction negative k Lt. Okay, seen these all the time, but the deal is that's on the amount remaining, because BOD is just such a weird term to use in the first place that we need this BOD remaining. So then we can integrate that and get Lt equals L naught times e to the minus kt. So we've done hundreds of times, where k is the BOD reaction rate constant and per day. And like I said, L naught is Lt plus BOD at some time t. So L naught, really, we define that as what happens as soon as we mix the wastewater with the river water. Okay, so that's almost everything for the deoxygenation side. We just need to add one more piece, because this is not actually a rate of deoxygenation. That's a rate of change for the amount of food remaining, right? So the rate of deoxygenation then has to do with some rate constant, Kd, for deoxygenation rate constant, some typical values out there in the literature. And so then we could say the rate at which deoxygenation occurs is equal to Kd times that L naught, the total that was there, times e to the minus k dt. So not going to bother deriving that. That's just an equation that we have. I don't think you'll even need to use that, but that goes into the subsequent integration that I'll show you. Okay, so that's all for the deoxygenation side, and we have some understanding now of where that's coming from, and at least where that L naught is coming from. That's maybe more like something that you'll need to be able to solve for, the L naught. So on the physical side, the reaeration is going to occur based on gas transfer across the liquid barrier. And it's going to be proportional to how much oxygen is missing. So again, with the strange seeming units, the rate at which that's going to happen is going to depend on how much oxygen deficit we have. So we'll have maximum reaeration when we're at the minimum dissolved oxygen. So the reaeration rate we could describe as a growth equation, Kr times D, where Kr is that rate of reaeration, rate constant. D is the deficit, dissolved oxygen at saturation minus the dissolved oxygen at a given time. And we have an equation that defines the Kr, that reaeration rate constant, and that's basically an empirical equation. People have studied a lot of lakes and rivers and streams and come up with this parameter that says, well, if we know the speed of the river and we know the depth, or I guess maybe you could call it the height of the water column, then they should be proportional in some manner, right? So the equation goes like this. Well, after measuring thousands of these different ones, this equation makes a good line of best fit, right? It's 3.9 times u, which is the speed, to the 1/2 power, divided by the height of the water column to the 3/2 power. So just kind of arbitrary. It's just that seems to fit. So we have that equation. Okay, so if we know something about the height, or the depth rather, and the speed of the river, we're good to go. For example, sorry, I'm gonna skip that for the moment. So for example, the different water bodies here, we have a small pond, sluggish stream, large stream, swift streams, rapids, and waterfalls. You can imagine a waterfall is going to be providing a lot more aeration to the water than a slow-moving bayou, right? So these values are ranging from 0.1 per day to upwards of 1.15. So also kind of goes to show when you have a pond in just in your neighborhood or something in southern Louisiana, it's a pretty good idea to add a fountain so that the water doesn't go too stagnant, lose too much dissolved oxygen. You get anaerobic processes that tend to create lots of stinky stuff, and the lack of oxygen probably kills some things that are further going to contribute to the stink. So we like to keep a pond aerated for a variety of reasons, and it's just prettier that way anyway, right? Okay, so there's just a few ranges. Can imagine how those will play out. So as we model the amount of oxygen remaining in solution, we can take a look at two things here. First of all, the oxygen, kind of the rate of deoxygenation versus the rate of oxygenation, and compare that to the actual oxygen sag curve that I drew up earlier, right? We have some sag, we reach a minimum point. That's what we're kind of concerned about, want to know about, and later it will be restored to some extent. So early on, we have very high rate of deoxygenation. So it's the amount of oxygen being removed. It's being removed very quickly. That means almost immediately we start having reaeration. If we had fully saturated water with oxygen, the reaeration is 0. But since we didn't start with saturation point, we're not starting at 0 reaeration. So typically there's just constant reaeration because natural body of water is going to have some natural organic matter and stuff like that. So that's just going to drop like I drew the TOC. The rate of deoxygenation is going to follow essentially the same path that the organic matter, the food, is going to follow. So that's going to be following almost no deoxygenation here at the end. And then the rate of reaeration is going to be essentially inverse of the actual oxygen profile. Okay, so while we started with some deficit, we ramped up the deficit pretty high. And so we have a maximum rate of reaeration right there, right at the minimum dissolved oxygen or the maximum deficit. So we could take a look at this value here as the deficit, right? And this, in this case, that would be the maximum deficit at that point. Whereas then this is the maximum rate of reaeration. And then it's going to decrease after that as the oxygen value is restored. So that's kind of what's happening. And now I'd like to put it together. So we have D naught as the initial deficit, D as a deficit at some time t. So we can do dd, dt, and essentially this is going to be the deoxygenation rate minus the reaeration rate. All right, so this is those two components. Okay, so that'll give us, from our equations we just looked at, this kd times L naught times e to the minus kt, and this guy is minus kr times d. Because it's we're looking at the deficit, so it's like how much is missing is we have what's missing is the deoxygenation minus the reaeration. So it's kind of a weird way to look at it. That's the way it is. All right, so take a few minutes and integrate this. I'm just kidding. Let's let the book do that for us. Maybe I should have given you 20 seconds of effects there. Integrate. Do it.
Integrate with respect to that.
Yeah. Fortunately, the book has a nice solution for us. So we'll be thankful for that this week, right? So the integration apparently is kd times L naught divided by kr minus kd. And as we'll see, almost everything is these two terms, right? Plus the ultimate BOD there as well. So these guys times e to the minus kd times t minus e to the minus kr times t, all that plus d naught times e to the minus krt. So, as we might expect, we're basically seeing these parameters put forward in an integrated form. And if we take a look at, it's something times e to the minus something, right? That's pretty familiar. And we know that if we get into differential equations and things, we recognize a lot of this as that could make sense. I just don't have the math on hand to do that, right? Somebody else did that. Great. There is one problem, though. If we notice, if the rate constants happen to be the same here, kr and kd, we get a 0 in the denominator. So we actually need a second tool to estimate for those cases. So we have a second equation for d. Keep in mind this is specifically for only the cases where those happen to be equal. So I'm going to go ahead and give you both on the formula sheet. This one can be used, but should only be used when those two happen to be equal. That's the deficit is equal to kd L naught t plus d naught, all that times e to the minus kd t. All right. So with that, we have some understanding of the deficit. So the remaining thing is, okay, well, how do we find the maximum deficit, which is that critical point? And we're going to look to the book again to do that, to find the minimum there and get that value. So if we say xc is that critical distance downstream, the c being kind of critical, meaning that's the critical point we're interested in. U is the stream speed. Let's say this is in kilometers distance and kilometers per day will be typical. Then TC would be the time elapsed, how long it took for us to get water from the start to that critical point. Of course, we know from simple physics that our distance is going to be velocity times time, or we could calculate time as distance divided by velocity, right? So that's just kind of assumed that we can work with those pieces. Now, it turns out if we were to do sort of a maximization or minimization function of this, I guess max on deficit, right? To find the local maximum, again, book provided us a nice equation here. It'll look like this, where the time is going to be equal to 1 over kr minus kd, again with a problem if we happen to have equal rate constants. That's not equal rates, right? The rates will equal at some point inevitably, like we saw that on the this graph. The rates do meet and they do become equal at that critical point, but that's different than the rate constants themselves. So the rate constants might be equal. If so, I don't think we can do this analysis here with a TC like that, at least not this equation. The book doesn't give us another one that counts that out, so I won't be giving you a problem like that either. So that'll be that times the natural log of KR over KD times 1 minus D naught KR minus KD divided by KD L naught. Okay, so equations then basically here to describe that whole system where we have the rate of substrate, so substrate decreasing, therefore the rate of deoxygenation starts high, ends low. Rate of reaeration depends on how much oxygen is missing, and we can get a nice estimation of what happens downstream using all of that. Okay, so here's an example. I think what I'm going to do for you is let you off a little early for Thanksgiving. I'm just going to, this first example is really just asking us to estimate the dissolved oxygen of a mixture of two streams. So this is kind of starting off kind of on the easier side of stuff. So this would be a dissolved oxygen in the wastewater with some flow of wastewater, DO in the river with some river flow, and then we have some Q mixed and a DO mixed, right? And that's kind of what we're looking at. So that one's pretty straightforward. Feel free to solve that on your own. Probably pick up here after the break, and then have kind of maybe some other type of lecture, as I mentioned. But here, basically, this one gets into the equations we were just looking at, where we have, okay, find the time and distance downstream at which the oxygen deficit is at a maximum, and find the minimum value of dissolved oxygen. Okay, so I'll let you off with that. I'll be posting homework later today. Happy Thanksgiving. And I have exams if anybody needed to pick theirs up.